Suppose you have a vector space V, and suppose that you have a basis for V consisting of vectors v1 to vn. Then one of the things that we know about a basis is that every vector in the vector space can be uniquely expressed as a linear combination of the basis vectors. In fact, that is the thing to know about a basis. That's the reason that we care about bases in the first place. This process of going from V to the linear combination of the basis elements gives us a transformation that's called the coordinate transformation. If we call the basis B, then the coordinate transformation associated to B is the transformation that goes from V to Rn, which takes the element V and gives you the vector whose entries are the coefficients when you express V as a linear combination of the basis vectors. This should feel a little bit familiar to you because we have seen coordinate transformations before in the context where V was also Rn. But now we have a more general way of understanding it, which actually should shed more light on what we were doing back then. The idea is that by having a basis in your vector space, that gives you a way to coordinatize your vector space, to draw axes on your vector space, so you can address different elements of the vector space by its coordinates along those axes. This is a linear transformation. I'll go through the explanation of why it works with scalar multiplication, and I'll leave you to do the addition part. All right, so suppose LB of V is the vector C1 to Cn. What that means is that V is C1 times V1, and so on, all the way up to Cn times Vn. That is how the coordinate transformation is defined. So then if I take that equation and I multiply both sides by the scalar k, that gives me a way to write k times v as a linear combination of the basis vectors. And the coefficients that are in that equation tell us what the entries are in LB of kv. And now we can look at the result that we got and see that that's just k times LB of v. And so in the end, we've proved that it's possible to just pull the scalar out of a coordinate transformation, which is one of the things that you need to check in order to show that it's linear. Like I said, I'll leave you to do the other thing, which is to check that it works with addition. Okay, so let's look at an example. So remember that the standard basis for P2 just consists of the different powers of t. So 1, which is t to the 0, t, and t squared. Now, the general form for an element of P2 is P of t is a plus bt plus ct squared. So let's look at what happens when you take an element of P2 and put it into the coordinate transformation for the standard basis. Well, the key thing is that when you write P of t as at plus bt plus ct squared, you're writing it as a linear combination of the basis vectors. So the coefficients a, b, and c are exactly the entries in the vector that you get from the coordinate transformation. And so that's it. The coordinate transformation for the standard basis takes the polynomial a plus bt plus ct squared and produces the vector abc as output. But the standard basis isn't the only basis that you could use for P2. Another basis is this one, where you have 1, t minus 2, and t minus 2 squared. This is the basis that consists of powers of t minus 2 rather than powers of t. It would be more convenient for problems that involve analyzing functions in the vicinity of t equals 2. So now let's look at what happens when you apply the coordinate transformation for this basis to the polynomial a plus bt plus ct squared. Well, now the problem is that we don't have an expression that's in terms of linear combinations of the basis elements. So we can't just immediately see what the output of the coordinate transformation would be. But with a little bit of algebra, we can figure it out. Okay, so this is what P of t looks like if you rewrite it as a linear combination of these basis vectors. Don't worry too much about how I got this. It really was just some algebraic manipulation combined with trial and error. But just for your sake, so you can believe that it's true, you should maybe pause this video and expand the parentheses and check that it actually does simplify to a plus bt plus ct squared. But the point is that this does express p of t as something times 1 plus something times t minus 2 plus something times t minus 2 squared. So it is a linear combination of the basis vectors. And those coefficients are the entries of the vector that we get from the coordinate transformation. And so that gives us the formula for LB of p of t. Pop quiz. What is LB of t minus 2? Now, you could answer this question using the formula that we just found, and just plug in this case, b would be equal to 1 and a would be equal to minus 2, and then you would get the answer. But there's a simpler way to think about this, which comes back to the fundamental definition of what the coordinate transformation is. To find LB of t minus 2, what we would want to do is write t minus 2 as a linear combination of the basis vectors. But t minus 2 is one of the basis vectors. And so the way to write it as a linear combination of the basis vectors is to write it as 0 times 1 plus 1 times t minus 2 plus 0 times t minus 2 squared. And from that, you get the answer that LB of t minus 2 is 0, 1, 0. And similarly, LB of 1 is 1, 0, 0, and LB of t minus 2 squared is 0, 0, 1. This illustrates a general principle about the coordinate transformation, that what it really does is that it takes the basis vectors in V that you're using, and it transforms them into the standard basis vectors in Rn. So, an important fact about coordinate transformations is that they are invertible. And this is really something that you can see directly in the definition. If you give me the vector in Rn, then I can use the entries in that vector to produce a linear combination of the basis vectors in V. And on the other hand, if you give me the vector in V, I can uniquely write it as a linear combination of the basis vectors and produce the vector in Rn. And just so you know, there's a fancy word for invertible linear transformations, and that word is isomorphism. I probably will just say invertible, but it's good for you to know that word, isomorphism, because it's commonly used. Okay, now, suppose that T is a linear transformation from V to V. And suppose that you picked some basis B for V. Now I can use this information to draw a nice little diagram. So I've got T, which is a map that goes from V to V. But then I also have the coordinate transformation, which is a map from V to Rn. And I can apply that on both sides of this diagram. And so this is really interesting because I can now start in the lower left-hand corner of this diagram, apply LB inverse to get up to V, then apply T to go to the right side, and then apply LB to get back to Rn, and that is a composition of linear transformations and is therefore itself a linear transformation. But this is a linear transformation from Rn to Rn. So this green arrow that I just drew is really just a shortcut, which is supposed to do the same steps as going up and over and down, but do it all at once. But remember, there was something really important that we learned about linear transformations from Rn to Rn. And that's that there always is a corresponding matrix, where multiplying by that matrix is the same thing as performing the linear transformation. And so this matrix that we get is called the coordinate matrix of T with respect to B. And the notation that we use for it is where T is in a bracket with a little b subscript. All right, so I think this picture that I just drew with the diagram, it's a really lovely picture, and I think it really helps to explain where this thing comes from and why it is. But it's pretty abstract, and if we're going to actually use this idea in practice, then we're going to need to have a straightforward process for finding the matrix. So remember this, if you have a description of a linear transformation from Rn to Rn, and you want to find the matrix that corresponds to that linear transformation, the way to do it is to plug in the standard basis vectors, E1, E2, and so on, and see what you get. And whatever you get will make up the columns of the matrix. This is stuff that we were doing way back at the beginning of the semester, but it's still important. So let's use that idea to figure out how to get the coordinate matrix. So I'm starting by putting E1 on the lower left side of the diagram. And then we're going to see what happens as we apply the different transformations that get it to the lower right side of the diagram. So what happens when we take E1 and we go up using the inverse of the coordinate transformation? Well, as we saw earlier, the coordinate transformation LB relates the basis vectors in V to the standard basis vectors in Rn. So E1 gets related to V1 under the coordinate transformation. So when you go up, you get V1. So then we want to go to the right. And for this, we don't know anything special about t. T is just supposed to be any linear transformation from V to V. So all we can say is that the result is t of V1. And then from there, we want to apply the coordinate transformation to get back to Rn. So how do we do that? Well, the general procedure for computing a coordinate transformation is that you write your vector as a linear combination of the basis vectors, and then the coefficients are the entries in the vector that you get from the coordinate transformation. And so that gives us the process for finding this matrix. The first thing that you want to do is write T of V1 as a linear combination of the basis vectors V1 to Vn. And those coefficients are going to be the first column of the matrix. And then you do the same thing for V2, V3, and so on, and you get the other columns of the matrix. You do it all, and you've got the whole matrix. All right, so I know that this abstract picture might seem a little bit intense, but it's actually not that bad in practice, and so I'll show you an example so you can see how it works. Okay, so here's an example. Let t from P2 to P2 be given by this formula, that T of P is t times P prime of t plus t squared times P of 0. This is a linear transformation, and it's probably a good exercise for you to check that it's a linear transformation. But what we're going to do right now is find the coordinate matrix of t with respect to the standard basis. And remember that the standard basis for P2 consists of 1, t, and t squared. So the process for this is to go through each of the basis vectors, plug it into t, and then rewrite the result as a linear combination of the basis vectors again. And those coefficients will give you the columns of the matrix. So when we calculate t of 1, the derivative is 0, and p of 0 is 1, and so we get t squared. And then, of course, if we write t squared as a linear combination of 1t and t squared, that linear combination is 0 times 1 plus 0 times t plus 1 times t squared. So those numbers, 0, 0, and 1, become the first column of the matrix. And then to get the second column, we do the same thing for t. And so in this case, the derivative is 1, so we get t times 1, and p of 0 is 0, so it's just t times 1, so it's t. And then, of course, when you write t as a linear combination of the basis vectors, that's 0 times 1 plus 1 times t plus 0 times t squared. You'll be able to skip that step of writing it as 0 times 1 plus 1 times t plus 0 times t squared, but I'm writing it out here so you can see exactly where the numbers come from. So in this case, those numbers become the second column of the matrix. And then for the third column, we do the same thing for t squared. And so in this case, t times p prime of t is 2t squared, and p of 0 is 0, so you just have 2t squared. And so we write out 2t squared as a linear combination of the basis vectors, and then that gives us the third column of the matrix. So with the standard basis, the process of finding the matrix is fairly straightforward. And for other bases, it's no more difficult in theory. The only thing is that in that step where you compute t of the basis vector, and then you write that basis vector as a linear combination of the basis vectors again, there might be some solving that has to take place in order to do that. So the calculations in that step might be a little bit more involved, but conceptually, nothing changes. Okay, so now finally, the question that you've probably been asking for a while now is, what's the point of this? Why are we doing this? What is it good for? And the answer to that is that this allows us to turn problems involving linear transformations into matrix problems. And then once you have a matrix equation, you can solve it using the tools that we learned at the beginning of the semester, Gauss-Jordan elimination, stuff like that. So here's an example that illustrates this idea. The question is to find a solution in P2 to the differential equation y prime minus y is equal to x squared. If you remember, this equation actually came up in a recent lecture, and I just told you what the solution was without giving you any explanation of where it came from. This is actually how you find it. And so the idea of how we'll solve this is that we'll use the standard basis to turn the differential equation into a matrix equation. So the first thing is to observe that this differential equation can be rewritten as a linear equation, t of y equals x squared, where t of y is y prime minus y. That's a linear transformation. So then the next thing that we'll do is we'll find the matrix for t with respect to the standard basis. And so that's going through the steps that are similar to what we did in the previous slide. But I'll do it a little bit quicker this time. So first of all, t of 1 is minus 1, and then t of x is 1 minus x. And just as a side note, in this differential equation, the independent variable is x and not t, so the standard basis is 1x and x squared. And then finally, t of x squared is 2x minus x squared. And so from that first equation, t of 1 equals minus 1, we get the first column of the matrix, minus 1, 0, 0. From the second equation, t of x equals 1 minus x, we get the second column of the matrix, 1, minus 1, 0. And from the third equation, t of x squared equals 2x minus x squared, we get the third column of the matrix, 0, 2, minus 1. But to get a matrix equation, we also need to translate the right side of the equation into a vector. And for that, we use the coordinate transformation for the standard basis. And this is pretty easy because x squared is 0 times 1 plus 0 times x plus 1 times x squared. The coordinate vector is 0, 0, 1. And so now we have enough information to write down a matrix equation. And this is the matrix equation that represents the differential equation. In other words, we can solve the differential equation by solving this matrix equation. So this is an upper triangular matrix, and so it's actually not that bad to solve by hand, but you can also just write down the augmented matrix, put it into reduced echelon form, and get the solution. And so the solution is minus 2, minus 2, minus 1, but that's the solution as a vector. We want the solution as a function that solves the differential equation. And so to do that, we need to turn this vector back into an element of P2 using the coordinate transformation in the inverse direction. But that just means that we use the entries in this vector as the coefficients in the linear combination of the basis elements. So we have minus 2 times 1 plus minus 2 times x plus minus 1 times x squared. And that gives us the solution. Y is minus 2 minus 2x minus x squared. That solves the differential equation. And then finally, I'll note that this isn't the general solution to the differential equation. This is just a particular solution. But finding a particular solution is the first step toward finding the general solution. And so it's interesting that linear algebra gives you the overall framework of solving differential equations by finding a particular solution, solving the homogeneous equation, and then putting those solutions together. But linear algebra is also used in those individual steps. And what we just saw is how linear algebra is used to find particular solutions. Linear algebra also plays a role in the step of finding the homogeneous solution because we know that the homogeneous equation is a subspace. And so what that means is that if we find enough homogeneous solutions, we can take linear combinations to get all of them. And so seriously, it's not a stretch to say that the study of differential equations is just applied linear algebra.